So, do you think the guy's gonna come today?
I don't know. Yeah, he's supposed to come today.
Is that all? Oh, hey.
Here, I'm the interviewer.
You're here for the interview?
Yeah, and you're Dr. Tanaka.
Yeah, I'm Dr. Tanaka. I got a spare half hour. We can do this right now.
Alright, so Professor Tanaka, can you explain Charles's law for us?
Charles' law is a scientific law that states that volume and temperature, in terms of the gas, are directly proportional.
Can you give us an example of this law?
Okay, so let me explain to you this way. Okay, so let's say you have a gas at room temperature. If we were to raise the Celsius temperature of this gas by 1 Celsius, then it would cause the gas to expand. However, if we were to drop the Celsius temperature, then it would contract. In which case the volume would decrease, and in the other case, the volume would increase.
We're going to lower the temperature here in this bucket with dry ice, which is actually frozen carbon dioxide, negative 73 degrees Celsius.
So first we're going to cover the bottom layer with some dry ice, so the balloon is surrounded on the bottom. And just to reiterate, the balloon will only go down. It will only be smaller to a certain point. It will not be smaller even more.
Is this at standard pressure?
Yes, this is at standard atmosphere pressure.
This is harder than it looks. God. Alright. And now we wait.
When the particles are heated up, they gain kinetic energy. And the particles within the gas, since they gain kinetic energy, they need a lot larger volume in order to spread out, as they are now bouncing around everywhere. And it also works in the opposite. When they lose kinetic energy, they are not moving around as much, and thus will need less space to exist.
Okay, so basically we took a balloon and we placed it in a bucket full of dry ice, which is frozen carbon dioxide at negative 73 degrees Celsius. And at first it's at room temperature, so basically we dropped the temperature by 73 degrees. And by using this, basically the temperature dropped and the kinetic energy dropped. So the particles in there, they occupied less space. So that means the balloon got smaller in volume, which is just particles occupying space. So after we dropped the temperature, we observed the balloon decreasing in size. And then once we took it out, it resumed back into room temperature, and the volume increased again because the temperature increased from negative 73 degrees Celsius back to 0 degrees Celsius.
And all at standard pressure, right?
Oh, it was all at standard pressure too, because the atmosphere pressure did not change.